All right, my project is on hurricane modeling and prediction. I live in South Florida, so I am pretty familiar with the impacts of hurricane science and the ability of forecasters to predict where a hurricane will make landfall and the intensity at which they will do so, and the accuracy at which science can make these predictions is super important for people's safety and the safety of their property, and just generally ensuring a good quality of life for people who live, especially in poor areas that can be struck with these storms. So obviously this is going to be super important to try to get a more accurate cone and the most accurate sort of estimate that we can for where a hurricane will hit and how much damage it will do. So the research objective of this isn't to take in all of the data that you could take into account, because obviously this is going to be super complicated. It's a very chaotic system. You're going to have lots of small effects making big changes, and the data that's collected comes from buoys that are placed in different lattices across the globe, really, but oftentimes locally in the Atlantic, and then also airplane reconnaissance data, and satellite data as well. But just focusing on the buoy data for now, that's collected by the NOAA buoys in the Atlantic, and they have lots of ones that you can select from all these little yellow dots on this map. So we can kind of use this data and aggregate it in order to try to better understand how we can track an approaching storm. And we have four strategies for trying to do so. The first is how do we see the hurricane in the data? So looking at the data and trying to see it. And obviously the most obvious way is going to be by a spike in wind speed, right? The wind speed is probably the most obvious sign that a hurricane has come. And you can see that there's this time coordinate represents the progression through the month of August, and August 2017. And right at the end of the month, Hurricane Harvey strikes, and you see a spike for a couple of days, and then it all goes back down. And this data takes a little bit of processing, because the data that's given by the NOAA isn't totally clean. It has missing gaps, and the data is taken at different frequency intervals, so it's hard to average them all out and compare them. So you have to do like some interpolation that tries to guess the intermediate points, so you can get a smooth plot. But between all of the different buoys and all the different, you can get an average, and you can certainly see the hurricane in the data. So that's just the first step. And then in order to analyze the data, like to look at what's inside of it beyond just a spike, I did a Fourier decomposition, which is a form of frequency analysis that basically transforms a data set from the time and some other important data domain to the frequency versus amplitude domain. So the graph on the left here, we have a bunch of different frequencies that were found in this data. You see a lot of oscillations and inside frequencies that you can break down through this decomposition. And then plot the most common ones, and then also filter out ones that are too low, that are just noise. So the ones with the highest amplitude are the ones that we're really going to be concerned about, and those are the ones that are really spiking at the very top of the graph. And one of the highest frequency actually happens to be the diurnal frequency, how it changes by day and night, because the different different amount of heat that can be absorbed by the ocean really changes the all sorts of weather conditions or in the day and night. So the diurnal frequency becomes a huge driving factor. But there's other ones that we'd want to look at too, and we can even filter that one out to get a better sense of what the rest of the data is showing. So on the right, you can even transform this frequency data after you've filtered it back to the time versus wind speed domain, using an inverse Fourier transform, and you can see a much cleaner data set that just gives you just the frequencies that you want, in a certain range that you want to see. So that's the frequency analysis. Then something happened here, but the next step would be to look at how the hurricane actually moved, right? Because we see this other data about what happened to the wind speed, but how did it move through the space by time? And on the right is an actual map, but on the left is a heat map of the wind speeds that were measured at different points from the storm while it was happening, and then so inside of where the wind speed was 64 knots or above, it's white color, and then as you move further out with decreasing wind speeds, the color decreases into black. So you can kind of see the storm in this heat map, and you can look at how the implicit time coordinate here changes the width of the inner area and how it changed the spread of the storm. So we're starting at the bottom left and ending at the top right over here. And obviously it's going to be a mirror image because the latitude is increasing to the right, while in the right graph the latitude is increasing to the left because it's west latitudes. But beyond that, the graphs are nearly identical. So that's helpful there. And then you can plot this in color for one, but also in terms of where the wind speeds were above a certain value by instead of just using the actual wind speed data that's collected, but modeling it based off of different mathematical models for the storm. So one is that wind speed is K over R, where K is a constant about the net flow of the fluid, namely the wind speed, and R is the distance from the storm. And you see this gives a track that's about what we had. But then if you try other models like K equals K over the square root of R or K over R squared, you get data that doesn't really match up, like a storm that's too thin or a much wider region that's affected than really was affected. So the K over R model really fits, and that fits with the math too. If you combine the mathematics of a vortex flow, which is the fluid that's spinning around the wind, and then also the sink flow, the fact that the wind is moving inward. So you have both of these flows that are occurring at the same time to create a net flow, and together it is inversely proportional to the distance from the storm. And you can use this to run different sorts of regressions on the data. So one of them is, for example, a circular regression is what I call it, where you can use the distance formula and create regression coefficients that if you have a bunch of different locations for buoys in the form of XY values and then corresponding wind speed values collected at the buoys, you can regress to the center of the storm by finding the multiple regression coefficients and then plot those. You can do a similar thing, and you see this right here. The left graph here is circular regression, and it kind of fits the graph, the plot that we saw earlier. It's not perfect, obviously, but it's more or less moving in the correct direction. You have the darker dots representing earlier measurements and lighter dots representing later measurements. And another form on the right is an experimental regression that I tried, which I called ray regression, which is where it basically found a ray that the center of the storm had to be on for each buoy by looking at the vector orthogonal to the wind speed, given that it's a counterclockwise fluid flow in the northern hemisphere. And then it finds a number of different lines that the arrays really in one direction that the center of the storm should be on, and then tries to identify where the center would best be from that data. And obviously this one's going to be a little more scattered, so maybe combining these techniques would yield something useful, and that's something that's still in progress, and such as climate science and in working with these chaotic systems, that there's always going to be a lot of uncertainty involved. But these different techniques can really help us to not only see the storm, but also understand and predict how it will behave in a concrete way, and think about how we might want to optimize where we put our measuring devices and our buoys in order to get the best sort of result out of our data. So yeah, thank you so much for listening. I hope you found this interesting. Thank you.